Good morning, students. Welcome to lecture number 7, that is numericals on vapor power cycle. Vapor power cycle is also called steam power plant or steam power cycle. Steam power cycles or vapor power cycle works on the principle of Rankine cycle, and there's this problem, this numerical, as taken from VTU question paper. It is important and it is asked for 3 to 4 times. So let us read a definition of the problem. So in a Rankine cycle, the steam at inlet to the turbine is saturated at a pressure of 35 bar and exhaust pressure is zero point 0.2 bar. Assume flow rate 9.5 kg per second. Flow rate is nothing but it is a mass flow rate of steam, and determine the pump work, turbine work, that is work done by the turbine, Rankine efficiency, condenser heat flow, that is heat rejected in the condenser, and last one, the dryness at the end of expansion. Okay, dear students, in the previous lectures we discussed that to solve a numericals on vapor power cycle, in the problem he must give the three minimum data. One is in the maximum pressure, that is boiler pressure, and the minimum pressure of the cycle, that is condenser pressure, and one more data is the condition of steam at inlet to the turbine or at exhaust of the turbine. So here they are given three data. Sufficient data is given here. He has given my boiler pressure as well, condenser pressure, as well as he has used the word the steam at inlet to the turbine is saturated. Okay, so point number one, the point which steam is passes to the turbine should be on a dry line. Okay, now first what you have done, step number one, given data. So before solving or writing the given data, we will draw one TS diagram, simple TS diagram. So now I have taken one TS diagram here, temperature on y-axis, entropy on x-axis, and saturated liquid line, and this is saturated vapor line, which is called dry line, or it is also called liquid line is called wet line. Okay, now so in the definition of the problem he said that inlet to the turbine is saturated. So in this TS diagram I have taken point number one is inlet to the turbine, because 1 to 2 is expansion takes place in the turbine. So point number one is inlet to the turbine and is dry saturated. That is the reason the point number one I have taken on this dry line. If any problems in the numericals, if we said the inlet to the turbine or the steam which is entering to the turbine is wet, then it should be between these two curved lines. If it is superheated, then on the right side of this dry line. Understood? So point number one I have taken on this dry line. So 1 to 2 is expansion, that is isentropic expansion, or it is also called reversible adiabatic. So during this process entropy is constant, S1 is equal to S2. Remember this point. Then here I have written the component process also. In the turbine 1 to 2 process, the 2 to 3 process is called in the condenser, 3 to 4 process is pump, and 4 to 1 is boiler. And dear students, from point number 4 to point number 1 it is heat supplied at constant pressure. Okay, here we have written some data, given data. What he has given, the boiler pressure P1, that is 35 bar, and dear students, out of 2 the maximum pressure will be boiler pressure, the minimum pressure will be condenser pressure, that is a hint, and mass flow rate is 9.5 kg per second. So in the data he has given one quality of steam or condition of steam at inlet to the turbine, that is x1 we will take, x1 is equal to 1. That is dry we have written here. That is in the unknown section. So next, what he has asked, work done on the pump, WP is how much, then Rankine cycle efficiency is how much, and one more data is as work done by the turbine also, then heat rejected is how much in the condenser, then x2 is equal to how much. X2, what is x2? X2, this is point number 2, the quality of steam or the condition of steam at exit of the turbine here was. So exit of the turbine is point number 2, so x2 is equal to how much. Okay, now to solve these such type of numericals, so we have to refer a thermodynamic data handbook or steam table book. So at 35 pressure, I have noted down all the values which is given in the steam table, including saturation temperature, HF, that is enthalpy of fluid and gas. Enthalpy of gas is nothing but just purely steam, and just an entropy of water, that is fluid, entropy of both fluid and gas, and S entropy of gas, and V stands for specific volume of fluid, that is water, and specific volume of gas. Similarly, at both 35 and zero point 0.2 bar, I have taken values. The values are listed here. So here written from data handbook, steam table book. Okay. So next step is you have to find the enthalpies at all the points. All the points is, for example, point number 1, H1, H2, H3, H4. All 4 enthalpies you have to find out first. Then you'll substitute in the respective equations to calculate the unknowns. So next point is here, step number 3, the pump work. The first unknown what he has asked is pump work. So simultaneously we'll calculate enthalpies as well as the unknown parameters. The pump work is defined as work done by the pump on the pump is equal to difference in pressure, that is P1 minus P2, or boiler pressure minus condenser pressure multiplied by specific volume of fluid. You can ask a question, sir, why you have taken specific volume of fluid only? Why you have not taken VG? Here I have written VG and I have cross mark. Don't take VG because the pump in which the working fluid is water. So here I will go to TS diagram. So 3 to 4 process is pump work. Here the working fluid is water. It is not steam, or it is not mixture of both steam and water. Understood? So that is the reason VF we have taken. VF. So P1 is given as 35 bar. So 1 bar is 10 to the power of 5. So 35 into 10 to the power of 5 Pascal minus P2 is zero point 0.2 bar. So zero point 0.2 into 10 power of 5. The VF value you have taken from the data handbook was written as it is. So after doing mathematical operations, you will get 3539.8 joule per kg. Understood? So 3.5 kilojoule, just divided by 1000 to convert joule into kilojoule. And this is for 1 kg, as you can see the unit kilojoule per kg. But in the given problem, is asked for what is the value of work done on the pump for 9.5 kg. So 9.5 you have to multiply with this 3.53, you will get the total work done on the pump is 33.53 kilowatt. So to solve work done on the pump, we don't require any enthalpies, so it will be easily calculated using pressure difference and specific volume. So now go to next unknown, turbine work. Turbine work is nothing but work done by the turbine during expansion process. So work done by the turbine is equal to m dot. So if m is given, then you will take the whatever the value has given. If m dot, that is mass flow rate, is not given, then we'll assume that m is equal to 1. Okay, into h1 minus h2. That is turbine in which the work expansion is taking place. There is 1 to 2 process. So 1 to in 1 to 2, it goes to TS diagram. So So 1 to 2 expansion. So highest enthalpy will be at point number 1 and lowest enthalpy will be at point number 2. So difference between highest enthalpy and lowest enthalpy, and here we get the work done by the turbine. So H1 minus H2. H1, the point number 1 is on dry line, that is vapor line. Here it is on vapor line. So directly we will get the value of Hg. And dear students, I will make it clear, any values which is or you are taking on dry line, that it will be represented with suffix g. For example, if you are taking entropy on this dry line, that is Sg. If you are taking specific volume at this line, it is Vg. If you are taking enthalpy on this line, then it is Hg. So here point number 1 is located on this dry line, so directly it will become Hg. So Hg is equal to H1 at 35 bar. Why it is 35 bar is nothing but, look at this diagram. So 4 to 1 is boiler pressure. So point number 4 is also 35, here is also 35, here is also 35. So each point is 35. So point number 1 will be 35 bar. So here, so at 35 bar, you take the value of H1 using data handbook, that is 2802.0 kilojoule per kg. So H1 you got, but H2. Now to calculate H2, and dear students, look at this point. Point number 2 is either it is not on liquid line or it is not on vapor line. It is not x is equal to 0 or x is equal to 1. So the value of x between at point number 2 is between 0 and 1. So we don't know the value of x2, and at the same time we don't know the value of H2, enthalpy at point number 2. So enthalpy at point number 2 will be calculated H2. See, H2 is equal to HF. This is HF, enthalpy of fluid, plus and HFG. So right here, H2 is equal to HF X into HFG. Now, point number 2 is related to condenser pressure, that is second pressure. So I will take 2, 2, 2. Some books they will reserve 2 is nothing but point number 2. At the same time, it will also reflect it is condenser pressure. Okay, so H2 is equal to HF2 X2 HFG2. That you take equation number 2. Now to calculate H2, X2 is unknown. He has not given the value. Actually, he has asked the value of X2. X2 is nothing but the point number 2 is nothing but it is a exhaust point of the turbine. It is not inlet. Point number 1 is inlet. Point number 2 is outlet. So point here he has asked the dryness at the end of expansion. That is nothing but X2. So here X2 is unknown, so that we cannot calculate H2. The value of HF2, enthalpy at point number 2, here is equal to sum of these two we are written here. Now dear students, process 1 to 2 is reversible, adiabatic, or it is also called isentropic process. So during in isentropic process, entropy is constant, that is S1 is equal to S2. So now the same equation number 2 I will write for entropy. So S1 is directly, because it is dry steam, we get from the data handbook. So S1 I got 6.1229. Okay, here because S1 is equal to Sg, that is dry saturated steam. S2, same equation number 2 I have written as in terms of entropy. So SF2 plus X2 SFG2. SF2 is the entropy of fluid at second pressure, that is condenser pressure. The reason is point number 2 is condenser pressure. At the same time, point number 3 is also condenser pressure. So 2 to 3 pressure is constant, that is 0.1 bar. So at 0.1 bar, you have taken the values from the data handbook. here SF at 0.2 bar, that is second point, is how much? 0.8329. So here we have written 0.832, okay, plus x2 as it is. SFG2, similarly we have at point number 2, that is 0.2 bar, we have taken the value of entropy of mixture of both fluid and gas, because point number 2 is not pure vapor, it is not pure water, so it is mixture of both. So entropy value is 7.0773. So after doing some equation, once you solve this equation, you will get the value of x2 is 0.747. Okay, what does it mean? 74% of steam, remaining percent is water. That is the reason point number 2 is nearer to the vapor line. Percentage of steam, percentage of vapor is more, so it is nearer to here. Next, from equation number 2, now once you calculate the x2, you substitute here, you will get the value of h2, that is h2 is equal to 251.5. 251.5 is the enthalpy of fluid at condenser pressure, that is point number 2. Similarly x2, whatever the value you got here, you write it here, and HFG2 value is 2358.4 here. So once you calculate, simplify this equation and substitute all parameters in the calculator, you get the value of S2 is 2013.2, that is kilojoule per kg. So both H1 and H2 values, H1 and H2 values, you substitute in equation number 1. The equation number 1 you have taken as m dot H1 minus H2. So here substitute in equation number 1, the m dot is 9.5, the remaining H1 and H2 you substitute, you will get the value of WT, that is 7493.6 kilowatt. This is the second unknown calculated. Next, what is asked? Rankine efficiency. The Rankine efficiency is given as WT, work done by the turbine minus work done on the pump divided by heat supplied. This I have taken equation number 3. Work done on the pump you have calculated already. Work done on the turbine also you have calculated. But heat supplied we have not calculated. So calculate heats supplied. Again I have drawn TS diagram here. So heat supplied is between 4 to 1. So this downward arrow mark shows heat supply, that is in the boiler. So 4 is the starting point of heat addition and point number 1 is end point of heat addition. So between 1 and 4, the point number 1 temperature is more, so enthalpy will be more. So H1 minus H4 multiplied by mass will give the heat supplied. Heat supplied m dot s into H1 minus H4. M dot s value is given 9.5. H1 also already have taken from the data handbook at point number 1, that is dry steam, but H4 is not given. So you have to calculate H4. Dear students, just observe carefully. The point number 4 is here. So from this point to this point is H4. So H4 is equal to H3 plus pump work. 3 to 4 is pump work. So pump work plus H3 will give the value of H4. So H4 is equal to S3 plus work done on the pump. Okay. So H3 already you have calculated or you taken from the data handbook. S3 value will get directly from the data handbook. The reason is point number 3 is located on water line. So at water line, at this pressure, P2 pressure, you will get the value of HF. So 0.2 bar here, H3 is equal to HF at 0.2 bar. Sir, why you can ask a question, why HF, sir? Why not HFG or HG? HF nothing but point number 3 is purely on water line, no question of gas, no question of mixture of both. So HF at P2 pressure, that is H3. S3 is equal to HF. And work done on the pump, already you have determined 3.53. Substitute both the values, calculate H4, that is 255.03 will get. That is kilojoule per kg. Once all values are substitute here, then we can calculate QS. We will get 24198.2 kilowatt. So one student has asked in the discussion, so why how it has got kilowatt. Dear students, simplify the equation and substitute the units. What is the unit of m dot s? That is kg per second. Multiply. What is the difference between these two? These two are enthalpy difference. H1 minus H4. This is kilojoule per kg minus kilojoule per kg. Kilojoule per kg minus kilojoule per kg is again kilojoule per kg. Kg get cancelled. So kilojoule per second. Kilo as it is, joule per second is watt. And you remember any value if you multiply with mass flow rate kg per second to the kilojoule per kg, it will become kilowatt. So from equation number 3, that is Rankine cycle. Here equation number 3 is Rankine cycle. So Rankine cycle is equal to work done by the turbine minus work done on the pump divided by heat supplied, you will get 0.308. So if you put in terms of percentage, it is 30.8. And dear students, the maximum efficiency of the cycle in the steam power plant on the vapor power cell in the range of 35 to 45 maximum. It will not exceed more than that. Due to some calculator mistake, if you got the value 70, 80 or 90 something, assume that something you have done mistake. So 30 to 45. Okay, that is the efficiency of Rankine cycle. Okay. So last, and he has asked condenser heat flow. That is step number 6. Heat rejected in condenser. So condenser is 2 to 3 process. So 2 to 3 is condenser. So m dot s into H2 minus H3. So H2 is 2013 minus H3 is 251.5. You can ask questions, or why H2 minus H3, sir? It is because it is perfectly horizontal. 2 to 3 is horizontal process. Pressure is also same. Both the point number 2 and point number 3 are at constant pressure, that is 0.2 bar. Okay, but we have written H2 minus H3. Dear students, just you observe carefully here. At point number 2, it is percentage of steam is more. As the steam is flowing in the condenser, the steam is condensed to liquid at point number 3. The all steam is converted into liquid. That is called condensation process. That is the reason at point number 2, heat content is more, so obviously enthalpy will be more. That is the reason S2 minus H3. This is the advantages of Rankine cycle. But in the Carnot cycle, the it will start from point 2, but it will not end on the liquid line. Somewhere in the middle, it will stop and it will take to the boiler. Okay, that is not possible practically. So in the steam power plant, once the steam which came outside the turbine, that is point number 2, entire steam will be converted into water. Then it will be pumped to boiler. So that is the reason S2 minus S3 here. So all values already are calculated. Substitute the values. H3 is equal to HF2. As I told you, point number 3 is located on water line. So and point number 3 is related to condenser pressure. So at condenser pressure, HF value is 251.5. Sir, you have written H3 is equal to HF2. Why not HF3? Because point 2 and point 3 both are related to same pressure. Only the difference is position. But point number 3 is on water line, so HF. Okay. So last one, step number 7, dryness fraction at the end of expansion. Directly I have written x2 is equal to 0.747 because we have calculated in the step number 2. here see x2 is equal to 0.747 already we have calculated in the step number 4, sorry, step number 4. So x2 we have written here, x2 is equal to 0.747. So this is one type of numericals.